Hi everyone, today we're going to talk about the transformation of absolute value functions. In this new unit, we're going to focus specifically on absolute value functions. If you remember from last unit, the absolute value function looks like a V, right? That is the function that we're going to be focusing on. Now, we spoke about transformations, we spoke about domain and range, we spoke about a lot of things in the previous unit, and all we're going to do now is focus all of our energy with the same things, but now on just this function. So, let's get started. Before we begin, remember we already spoke about transformations, and this is a quick recap. The A is the value that either tells you if it's pointing up or pointing down. The A also tells you if it's being stretched or if it's being compressed. The C moves the function left and right, and it's always the opposite, right? If it's minus C, it moves to the right. If it's plus C, it moves to the left. And lastly, the plus D moves the function up or down. If it's positive, it goes up. If it's minus, it goes down. It moves the entire function downward. So how is this different? Well, we're just going to focus on one function, as I said earlier. So this is what we're going to see. We're going to focus on the A value of the absolute value of x minus C plus D. Again, this is the only function we're going to focus on for this actual next unit. So if you got a pretty good understanding about this one on the last unit, we're just going to do the same thing, but just with the letter V, or the function that looks like the letter V. So we're going to do 3 actual examples today. I'm going to give you either a graph, an equation, or a description, and using those 3 different things, we're going to want to be able to describe what kind of transformation it went through. So here are the 3 examples. Let's start with the first one. Here we have the original parent function. The original parent function, I'll write this in a different color, is f of x equals the absolute value of x. It goes through the origin, and it goes through 1 over 1 comma 1, it goes through those points. Notice how this function is a transformation. This is how it changed to the new function. So we want to be able to describe what happened here from here to here, and what is the equation of the new function. So let's start with the description. Notice how the vertex starts at 0, 0, and it moved 2 units to the left. Also, notice how this one is wider than this one. And that's really the 2 things that it went through. So let's just say that real quick. We can start by saying it shifted 2 units to the left. It didn't move up or down, so we're not going to worry about that part. It's just to the left. The next thing that it did is that it became wider. Now, by what factor? How much wider? And this is where it kicks in. We're going to start at the vertex, and we're going to check the slope. Up 1 over 2. 1 over 2. Up 1 over 2 means that the compression it went through is 1/2. So we say vertical compression of 1/2. And that's the transformation. So now we just have to do is write the equation given this information. Remember that the original equation is f of x equals a x minus c plus k. The compression of 1/2 is the a value. So we can just write f of x equals 1/2. The absolute value inside, remember, it moves it opposite. So the x minus c moves it to the right. If this is going to the left, it means it's going to be x plus 2. It's the opposite behavior. So I'm going to write that in blue. X plus 2. And since this function did not move up or down, we technically don't even have to put a plus k. But if you want, you could put plus 0 at the very end, because that's how up or down it's moving. Since it's not moving, we don't have to worry about that last piece. And this is it. This is our equation of the new graph. This is the description that it went through from here to here. And that's really it, guys. Let's do 2 more examples. Here I give you the equation. F of x equals 3x plus 1 minus 2. We want to be able to graph it and describe what it went through. Remember, this first point right here tells you if it's pointing up, pointing down, and if it's a stretch or a compression. Since 3 is bigger than 1, we're going to say that this becomes a vertical stretch. So let's start with that scenario. We can just say, in short term, vertical stretch by a factor of 3. The rest of the function, this moves it to the left and to the right. Remember, it's the opposite behavior. If it's plus 1, it moves it to the left. If it's minus 1, it moves it to the right. So this positive 1 moves it to the left 1 unit. So we say moves 1 unit to the left. Over here, this minus 2 moves it up or down. Since it's negative, we just follow the directions that it's given. The minus 2 means it moves it down 2 units. And 2 units down. And now that we've been able to describe that it's being stretched by 3 and it moves 1 to the left and 2 to down, we can actually go about graphing it. Remember, the original parent function starts at 0, 0. So if it moves 1 unit to the left, we're going to start here, and 2 units down, we're going to start at that location, at -1, comma, -2. Notice how here the vertex moves 1 to the left and 2 down, and now we get to talk about the vertical stretch by a factor of 3. Remember, this stretch, this factor of 3, is really more like the slope. Since it's a perfectly symmetrical v, these are straight lines, so we can actually treat it as a slope. And since the slope is 3, we can say the slope is actually 3 over 1. So we're going to go up 3, 1, 2, 3, over 1. And my point is going to be located right here. Now, since this is a v we're talking about, this is symmetrical. So we went up 3 over 1. We can do the same thing to the other side. So up 1, 2, 3, and then go to the left. This is as close as I can do it with my pretty fat finger. So this is your v. It's symmetrical. The origin moved 1 to the left and 2 down. Remember, it starts at 0, 0, so 1 to the left, 2 down. We start there, and then we counter slope. The slope is 3 over 1, so we go up 1, 2, 3 over 1, and then over 1 to the left, because this is a symmetrical function, and our v is going to be centered in that direction. Since 3 is positive, it's pointing up. If 3 were negative, the v would be pointing downward. All right, let's try one last example, and hopefully this is enough. So here we're given the description. The absolute value parent function is reflected over the x-axis, shifts 3 units to the right, and 2 units up. We want to be able to write the equation and draw the picture of that transformation that it went through. So let's talk about that. Let's start with the equation. Remember, the original parent function, or the original transformation function, we have the a x minus c plus k. The a tells you if it's pointing up or pointing down, and it also tells you like the slope per se. Since the function was reflected over the x-axis, that means that this became a negative number. So I'm going to write my function as f of x. Let's put it over here on the side, or below. F of x equals -1. I'm making it a -1 because it is being, it is being reflected over the x-axis, meaning the graph is going to flip downward. So this has to be a negative number. Technically it's a -1. I'm not going to put the 1 because -1 is just negative, right? It's the same thing. The minus c moves it to the left and to the right. Since this moves 3 units to the right, it's got to be the opposite, right? So it's going to be x minus 3. And then since this talks about moving 2 units up, we're going to do plus 2. And this is our function. F of x equals negative 1, absolute value of x minus 3 plus 2. So let's graph it. Let's see what this looks like. Remember, if it's moving 3 to the right and 2 units up, let's start with that point. Our original point starts here at the origin, right? So let's move this 3 to the right. 1, 2, 3, and then 2 up. 1, 2. So that's going to be my origin now. That's where we start. And now the v is going to start at that point. Now, since this function was reflected over the x-axis, this means that the v is going to go downward. Now, how do we check the slope? Well, since it was just reflected and it wasn't stretched or compressed, this negative 1 is my slope. So my slope is negative 1 over 1. So I'm going to go down 1 over 1. Down 1 over 1. And I have half of my v over here. On the left, the other half of the v goes down 1 over 1 to the other side. Down 1 over 1 to the other side. And we have the other half of the v, where the slope here is negative 1 over 1. That's why the function is pointing downward, and it moves 3 to the right and 2 up. This is it, guys. This is really it with transformations. If you can write the equation, if you can write a description, or if you can do the graph, then you really get this full understanding of transformations of absolute value functions. As long as you remember that absolute value functions are symmetrical and they will always be in a perfect V, whatever slope you have to the right, you'll have the same slope to the left. And yeah, this is it. We'll talk to you guys again tomorrow. And as always, I'll calculate later.